Okay, let's do some slightly more complicated kinematics problems. A box is resting against a tightly coiled spring. The spring is released, accelerating the ball to the right with acceleration 3.6 meters per second, 4.8 seconds. When the box is done being accelerated by the spring, it travels 12 meters on a slick surface on which friction is negligible and therefore maintains a constant velocity. After this 12-meter stretch, however, there should be another comma there, my bad, it goes onto a rougher surface and begins to slow down due to friction on the surface. This slowing down occurs with acceleration of magnitude 1.5 meters per second. Question number one, what is the maximum speed of the box during this entire process? You should keep in mind that there are two real things happening here where the speed of the box is changing. There's a speeding up when it's getting launched by the spring, and there's a slowing down when it's moving across the rough surface and losing its velocity. So the maximum speed of the box during the process should be, now this is a what question, it's not a when question, so we will have to give calculations, but this will be timed to be at the end of the spring's acceleration. So that's how we can set the parameters here. We want to look at from the beginning of when the spring starts to uncoil and accelerate the box, and the end of the speeding up, that will be when it attains its maximum speed. The reason for this hint is the maximum speed is sustained for a certain period of time. It's not just for one instant. Think about what happens after the box is accelerated by the spring. Well, yeah, it accelerates to the right, but then the first thing that it does is it travels over a slick surface that doesn't slow it down. So whatever the initial maximum speed is, that speed is actually sustained for several seconds as it glides over this really smooth surface, not slowing down. But what we're interested in is what is the speed after the spring speeds it up? So the spring speeds up the box. We know that the acceleration is 3.6 meters per second squared. We know that the time for which that acceleration is applied is 0.8 seconds. We don't know how far it travels during that time. We do, however, know that the initial velocity is 0 because the box is resting against a tightly coiled spring. That means it begins from rest. It begins from 0 velocity. So think about what type of question you want to answer. What is the maximum speed of the box? This is a question about velocities, right? Cool. So we want this equation. Final velocity equals initial velocity plus acceleration times time. How fast you're going now is how fast you used to be going plus how much you've sped up or slowed down. VF, that's what we want to solve for. Luckily, we know that this is 0, and we also happen to know the acceleration and the time. This is easy. This is 0 plus 3.6 times 0.8. And let me see, what is that? Let me get out a calculator. 3.6 times 0.8 is 2.88. And it is a velocity, so we should be writing it as meters per second. So what is the maximum speed of the box during this entire process? It's at the end of the spring's acceleration in principle, and then we go to calculate it, and we say that that will be 2.88 meters per second. Okay. So what's the next question? How far does the box travel while the spring is accelerating it? Focusing on this one now. While the spring is accelerating it, this means that we're going to be solving for the delta x during this interval. So I probably should have kept those quantities there, but they're not hard to write down again. The acceleration is once more 3.6. The time is 0.8. Delta x is unknown, but we want to know it. V initial is 0. VF is 2.88. We know that now. We're interested in a how far question, right? So think about the fact that this question does not depend on time. There is a kinematics equation that doesn't involve time, and it's this one. VF squared equals V naught squared plus 2A. On your formula sheet, it is, let's see, X minus X naught. Okay, that's for chumps. That's delta X. So you should be writing 2A and then delta X. No parentheses required. 2A delta X. Look at what we know and what we don't know in this equation. We do know VF. We do know V naught. We do know A. We don't know X or delta X. But because it's the one thing we don't know, that means we can solve for it, and that's the point. So we'll put in what we know. 2.88 squared equals 0 squared, so we don't need to write that, times 2A, that's 2 times 3.6, that's 7.2, times delta X, that means delta X equals 2.88 squared over 7.2. And let me see, divided by 7.2 is 1.152. 1.152 meters. Next question, how long does the box travel? As in, what is the length of time that the box travels on the frictionless surface? See how I'm building what I know about this. I used to not know the delta X. I used to not know the VF. Now I know both of those things. Oh, oops, sorry, I'm talking about the wrong period, because I already knew the time that the spring was accelerating it. But how long does it travel on the frictionless surface? For this setup, I'm going to need to take into account the fact that the velocity on the entire frictionless surface is this 2.88 that I calculated before. On the frictionless surface, it's not speeding up and it's not slowing down. That means that it has the 2.88 the whole time, not just initial or final, but the whole time. So on the frictionless surface, V the whole time is 2.88 meters per second. The time is unknown. The displacement we already know is 12 meters. That's given to us in the problem. It travels 12 meters on a slick surface. This isn't even really very much of a physics problem, because all you have is distance equals rate times time. So delta X equals, the kind of physicsy equation here is V average times time. But V average, if the velocity is constant, then that means V average is whatever that constant velocity is. So putting in what we know, this is 12 meters equals 2.88 times the time. And then I get that time is equal to 12 over 2.88. 12 divided by 2.88 is 4.16, repeating. I'm going to round that to 4.17 seconds, because more than 100th of a second, come on, like thousandths of a second, and nobody cares about that. And yeah, I know I measured this down to 1,000th of a meter, but fight me. So how long does the box travel on the frictionless surface? That's going to be 4.17 seconds. Okay. How long does it take for the box to come to a stop once it begins slowing down due to friction? Here I've got to put a couple new pieces together, because this is about a different circumstance. This says the initial velocity, initial velocity is 2.88, and the final velocity is going to be 0. Think about why. The final velocity is when it has stopped completely. That means the final velocity must be 0 because I'm looking for when it comes back to rest, That means 0 velocity. So initial velocity is 2.88, final velocity is 0. We already know this, don't we? No, I'm putting one over on you. The delta x we calculated before for each of those prior steps, but we didn't, we don't know this yet. So this is still unknown. But the acceleration is known. Acceleration of magnitude 1.5 meters per second squared. I'm going to make a mistake, and I'll give you a second to pick out what is wrong with that. So go. Tell me what's wrong with that. Right. That 1.5 needs to be negative, because if this and this point in the same direction, then that's speeding up. That's not slowing down. So the only way to get this right is to make sure that that has a negative sign in front of it. Cool? Cool. So how long does it take for the box to come to a stop? This is our old friend VF equals V naught plus AT, because we know most of the stuff in this equation. We know VF is 0. We know V naught is 2.88. We know A is negative 1.5, and that means we can solve for the time. So let's do that. VF is 0. V naught is 2.88. And the acceleration is 1.5, so that's minus 1.5 t. Rearrange just by subtracting 2.88 and dividing by negative 1.5, and you get t equals 2.88 divided by 1.5. Divided by 1.5, and that's 1.92 seconds. How long does it take for the box to come to a stop? That would be 1.92 seconds. Thank you very much. And the final question, how far does the box travel overall? So over the entire saga that we've described here. Well, think about the fact that we already know some of these. We know during acceleration, or well, I'll say during the spring. We already calculated that. That was back here. So that's 1.152 meters. And on the frictionless, that's 12 meters. That was given to us in the problem. And then on the friction part, this we actually didn't calculate, at least not yet. So this is the one thing that we still have to calculate. How far does it travel while it's slowing down on this friction full, if that's even a word, on this surface? So let's get the quantities written down one more time for that. Sorry if this is redundant. Negative 1.5 for the acceleration. We do not know the delta x. We do know that the initial velocity is 2.88. We know the final velocity is 0. And now we also happen to know the time is 1.92 seconds. So this is a good fit for either the time independent equation or the big granddaddy delta x equation. Because we haven't used that one before in this problem, I'm going to use that one. Delta x equals V naught t plus 1/2 AT squared. V naught is 2.88. Time is 1.92. 1/2 A would be minus 0.75, and that's times 1.92 squared. And now I really, really wish that I had my graphing calculator, but I don't. So hang on one second. This is 2.88 times 1.92 minus 0.75 times 1.92 squared. And that would be 2.7648. So that's in meters. So that means I can fill in, this is not the answer to the entire thing. It's the answer to just this part. So this is how far it travels during this stage. I'm going a little bit nuts with the number of decimal places. Nobody really measures down to the 10,000th place for meters, but I'm going to round it when I get all these put together. So put these together. 12 plus 2 is 14, plus 1 is 15. This is not going to make another meter. So that's going to be 15 point something. And then put these together, 152 plus this, that'll make it 926. No, 916. Yeah, 0.916 and then 8 meters. So about 15.92 meters. And there's your answer. There's a lot of stuff going on in this problem, but as long as you break it down into pieces, it becomes pretty manageable.